This recording covers terms, definitions, and simple problems related to the mass balance module with the chemical reactions. Students are advised to watch this tutorial before any attempt to solve mass balance problems with the chemical reactions. In the next few minutes, I will define and explain terms related to limiting reactant, fractional excess, conversion, fractional conversion, yield, and selectivity. In many chemical industrial processes, we do not follow a balanced stoichiometric equations. One of the reactants that we feed into the reactor is in excess, the other will be a limiting reactant. By the definition, limiting reactant or limiting reagent is that one that is first consumed completely if the reaction proceeds to completion. The other reactant is in excess. In this example, we have to calculate the mass of water that is produced when 8 grams of hydrogen and 24 grams of oxygen react. First, we have to balance the chemical reaction. 2 moles of hydrogen gas plus 1 mole of the oxygen gas would produce 2 moles of water as the liquid. In this example, we will have to find out whether hydrogen or oxygen is limiting reagent. Graphical representation of this reaction is shown on this slide, and we have two components. We have a hydrogen and we have oxygen, and as we can see, one of the figures here, the triangle, as the time progresses would be disappearing faster than the other component, and this blue component would become the excess reagent, whereas that one that would disappear first would be a limiting reagent. The red rectangle represents the water that is produced during the process. 8 grams of the hydrogen here would give us 3.968 moles, and this quantity, this number of moles, would be reacting with 24 grams of the hydrogen, which corresponds to 0.75 moles of the oxygen. At the beginning of the process, we don't have any product, so 0 moles of water would be produced. With the reaction progressing, we can see that 0.25 moles of oxygen is consumed and 0.5 moles of the hydrogen is utilized in the process. We have to look at the balance stoichiometry here. 2 moles of hydrogen per 1 mole of the oxygen are reacting inside the reactor. We will produce 0.5 moles of water. With the reaction taking place in the reactor, another 0.25 moles of oxygen is being consumed and 0.5 moles of hydrogen is being consumed. After a certain period of time that depends on the kinetics of the process, we will find out that oxygen would be the first reactant that would be disappearing inside the reactor, and we are left with 2.468 moles of the hydrogen. Therefore, the hydrogen would be the component that is in excess. At the end of the process, we will produce 1.5 moles of water. The approach in trying to find out the limiting and excess reactant can be summarized on this slide. The first step is to calculate the mass of the product that can be produced from the first reactant. We have to calculate the moles of the reactant. 8 grams of the hydrogen would give us 3.968 moles of the hydrogen. Calculate moles of the product. So 2 moles of the hydrogen would produce 2 moles of the water. So if we have 3.968 moles of the hydrogen, we will make 3.968 moles of water. When we multiply this number of moles by the molecular mass of water, 18 grams, we will end up with 71.4 grams of water. The next step is to calculate mass of that product that can be produced from the second reactant. So now we have to take 24 grams of the oxygen and repeat the same procedure. Calculate moles of the reactant. So 24 grams of oxygen divided by the molecular mass of the oxygen is equal to 0.75 moles of water. And the next step is to calculate the moles of the product. 1 mole of oxygen would give us 2 moles of liquid water. So for 0.75 moles of oxygen, we would produce 1.5 moles of the product water times molecular mass of the water. It will give us 27 grams of water. State the limiting reactant and corresponding mass of the product formed. The limiting reactant gives the least amount of the product. The actual mass of the product obtained from the chemical reaction is the lesser of the two product masses calculated in step 1 and step 2. So now we have to look at the masses of water, 71.4 grams of water versus 27 grams of water. 27 grams of water was made when oxygen was used, and this is the component that disappears from the reactor as the first one. Therefore, the oxygen would be a limiting reactant in the process. The next definition that we have to look at when we try to solve the problems related to the mass balances with the chemical reactions is the fractional excess of A. So the fractional of excess of A, which in most cases would be the limiting reactant, is equal to the ratio of number of moles of the reactant fed into the vessel minus number of moles of reactant A based on the balanced stoichiometric equation divided by the number of moles from the balanced stoichiometric equation. Fractional conversion. The fractional conversion F is defined as the ratio of moles reacted divided by the moles of the reactant fed into the reactor. Now we can look at the sample calculation. Here we can see a chemical reaction. C2H2 would react with 2 moles of H2 to make C2H6 ethane. From the actual process, we know that we feed 20 kilogram moles and 50 kilogram moles of the hydrogen, and we will make 20 kilogram moles of the product ethane. Which reactant is limiting, or which reactant is in excess? An alternative approach to trying to find the limiting reactant is to look at the actual feed into the reactor, and you can write down the stoichiometric quantities of each of these reactants based on the first reactant here, which is the C2H2. For 20 kilomoles of C2H2, we need twice as many moles of hydrogen. So for 20 kilomoles of C2H2, we need 40 kilogram moles of hydrogen, and stoichiometrically we will produce 20 kilomoles of the product. So when we look at these two numbers, 50 versus 40 kilogram moles, we can say that hydrogen is in excess in this reactor. We have 10 kilogram moles of hydrogen more than required based on the stoichiometry. Therefore, hydrogen would be in excess. The next question is, what would be the fractional excess in this process? Fractional excess obviously refers to the reactant which is in excess, and based on the definition we will have hydrogen fed into the reactor, actual quantities, minus 40 kilogram moles of the hydrogen from the balanced stoichiometric equation, divided by 40 kilogram moles of hydrogen, that's quantity coming out from the balanced chemical reaction. So 10 divided by 40 times 100% would give us 25%. So the fractional excess of the hydrogen is equal to 25%. Next question is, if the fractional conversion of C2H2 is equal to 90%, how much C2H2 is reacted. So the fractional conversion is given, which is 90%. Based on the definition, the fractional conversion F is the ratio of moles reacted divided by moles of the reactant fed into the reactor. So 0.9 would be equal to X divided by 20. X would be equal to 0.9 times 20, which is equal to 18 kilomoles. So this is the fractional conversion. When we look at the process flow diagram, we have 20 kilomoles of C2H2 fed into the reactor, and we convert 18 kilomoles of C2H6. Another definitions that we need to be familiar with include conversion, yield, and selectivity. If we have a chemical process, very often we have number of different competing reactions taking place inside of the reactor. So here we have an example of A plus B would produce C plus D, and then competing reaction C plus B would produce E plus D. If C is a desired product, then we want to minimize the second reaction because it uses up reactant B and desired product C. It also produces undesired product D. So when we assume that A would be a limiting reactant, conversion of A would be defined as the ratio of moles of A reacted divided by the moles of A reactant A fed into the reactor. And then we have conversion of B, which would be the ratio of moles of the B reacted divided by the moles of B fed into the chemical reactor. With the competing reactions taking place inside the chemical reactor, we very often will have to use the definition or term selectivity, and the selectivity is defined as the ratio of moles of C in the output. C is our green desired product, divided by the moles of E in the output, where E is undesired product. Definition of yield. Yield would be a ratio of moles of the desired products divided by the moles of A that we feed into the chemical reactor, assuming that we have 1:1 molar ratio of product to the reactant. In this case, we have 1 mole of A that would make 1 mole of C. Wider definition of yield is shown here. It will be the ratio of moles of the desired product or desired products divided by the moles that would have been formed if there were no side competing reactions and the limiting reactant would react completely. Examples would be shown during the in-class lecture.